Here we go. So, our next exam will be a week from today on Chapter 12, Chemical Kinetics. And we're going to do a review today. As soon as I get myself together here. Just pull this out. Easier to manipulate. You have a chance to look at the review document?
For chapter 12?
Chapter 12.
I skimmed it.
Okay.
And I actually got to look through it again.
Because that's what I'm going to be working from during the review. Review, here we go. I'm not going to start with number 1. Somehow or other, number 1 got shoved in there at the top of the list. And it's probably one of the more difficult problems. So we'll move toward the back of the line and see if we can pick up some simpler stuff before we jump into number 1. Let's see, how about okay. So let's but first of all, are there any questions or problems that we need? I want to be sure we handle them before I start talking. That way, I'll be sure I don't miss anything that's bothering you. Yeah, that's for today. I forgot to hand them out last week. My apologies. I hope we get done in time today in here so that we can do a little pre-lab discussion before we actually get to it.
Is this our lab for today? Or?
Yes, the actual lab is the first one we picked up.
Oh, okay.
These are supporting documents that help you with calculations.
Okay.
That's really the hard part of kinetics, is understanding the calculations. That's the real booger. The actual doing the lab is simple. But what do you do with the information once you're done?
Yeah.
Okay, so back to my question. Is there anything that's bothering anybody that we need to deal with before I go into a review? Okay. So let's start with basics. What's the
Is that exam the review that you're going over with for Exam2
right now?
or next week?
Next week.
Okay.
Yeah. Let's see, blue's not a good color to choose from. Let's try. Here's a black. That'll show up pretty good. What's the basic format of the rate law for a reaction? Right. Rate equals, right? The change in concentration of what did you say, A? A is a reactant divided by the change in time. So how does the concentration vary with time? And that's based upon A yields product. We really don't care about the product in most cases. We just want to see how fast does A disappear during this reaction. Now this is for a reaction which you only have one reactant. Right, so it's unimolecular.
So how do we express this as the rate law? So this is the general format. The rate law has a constant times the concentration of A to some power. So this is exactly what it says. It's a constant. This is the concentration of A, and this is the order. This is the order of A. If there's only one reactant, it's also the order of the reaction. If you have more than one reactant, say you have an A plus a B yields product, then your rate is equal to some constant times the order of A to the order n times B to the order n. In that case, n is the order of A still, and m is the order of B. The order of the reaction equals n plus n.
Okay. Those are just definitions. So what we want to do with respect to our lab today, we've actually got two components in the reaction. We've got the color, the food color, the dye, depending on which one you choose. Since we got a small group, you can either choose red or blue. So it'll be the concentration of that dye to some power times the concentration of the bleach to some power. So with respect to the color, it's a certain order, and with respect to bleach, it's a certain order. So we would write it like this, and this would be, let's just say you pick blue. Blue to the N, and bleach to the M. Okay, so that's a bimolecular reaction. You got bleach and the blue color. Okay. Now, does everybody remember, how do you study something like this? Because we've got orders of reactions that we've characterized based upon one reactant, like 0, 1, or 2. And what do they look like? But if you have two, how do you get around that? Well, the way we're going to do it is the concentration of bleach is so high that during the reaction, it doesn't change. Right? So it's constant. That means that this is constant and that's constant. So if we combine this one and that one to be some new constant, we call it K prime, and that's equal to K times the bleach to the N. So now we have that K prime, which is the pseudo rate constant, times our blue color to a power, to its order. Now we can study it and find out what the order of blue is. We're going to do that for two different concentrations of bleach, but they're both still high enough that they don't effectively change during the reaction. So we're going to have a K prime for one concentration of bleach and a K prime for the second concentration of bleach. And we should come up with the same N for both of them. But we'll have a different K prime because this changes. So that means this has to change too. So the first K prime, called K prime 1, and the second one is K prime 2. Then we'll talk about later what to do with those numbers. But we're going to be able to use those to tease out this value and these values. Actually, we're going to calculate bleach concentration under these two conditions. Okay, so let's, if you don't have any questions, we'll look at some problems now. In order to answer the next question, I think we need to put our basic information back up on the board. So our first order reaction, second order reaction, and third order reaction. Oh, duh. Nobody stopped me. Zero order, first order, second order. Okay. So, what does the zero order look like? If you plot against time, and time will always be on the x-axis for these plots. If you plot the concentration of A on this thing, it will decrease over time because it's being converted into something else, product, so it's disappearing. That means it has a negative slope. And the slope will be K. So the rate law then would be rate equals K, some K, times the concentration of A to the zero order, which is equal to K. So the rate is proportional to the constant, no matter what concentration you start at. Okay? Now, this line right here is the integrated rate law. So we're going to have concentration of A at any time is equal to K times, times time plus a zero. So it would cross this is the y-intercept, so it would cross this y-intercept here at a zero. And that makes sense, because at time zero, this is the concentration at the start. Like you're starting at time zero here. So that's the integrated rate law. Now what else can we get from this? The half-life. How long does it take for half of A to disappear? So the half-life for this one is, refresh my memory. Actually, that's not right. Oh, that was right, because that's the order. But this is A0. The beginning concentration divided by 2 divided by 2K. Okay, so that's the zero order. Now, what does the first order look like? Plotted against T. The straight line plot for this one is proportional not to A, but to the natural log of A. So that will give you a straight line with a negative slope. So in that case, the rate is equal to K times A to the first power, because it's first order. And the integrated rate law is the natural log of A equals, excuse me, I'll let this out, negative K. Is that right? Negative K. I think so. Or is K embedded with a negative? Losing my train of thought. 1 second. Yeah, it's negative. Negative K. This is negative K T plus natural log of A. Okay, so there the natural log of A crosses the y-intercept at time 0. Just like it did over here. But the half-life for this one is 0.693, I believe, divided by K. Is that right? Yeah. Okay, and then the last one. This one is the reciprocal of A. And this one has a positive slope. So these are both negative slopes. This one is a positive slope. And this rate is proportional to the constant times A to the second power. So the inverse of A is equal to K T plus the inverse of A 0. Okay, that's how you get the straight line out of that one. And the half-life equals 1 over K times the concentration of A. I think 0, 0, 0. So these two are proportional. These have proportionalities to A. This one does not. But question 4 says, for which order reaction is the half-life of the reaction proportional to 1 over K? This half-life is proportional to, what if we factor it out? So A 0 over 2 times 1 over K, right? That's valid in math and algebra, right? So this one's proportional to 1 over K. This one is also proportional to 1 over K. And this one is 1 over times 1 over K. They're all proportional to 1 over K. Any questions? Okay. How about, let's see. Well, number 5 is just to see if you know what a linear plot looks like for the different orders. So if it's a second order, number 5 says, which of the following will yield a linear plot? If it's second order, it has to be proportional T to 1 over A. So you look down here and say, all right, what is the A in this reaction? 2HI yields H2 plus I2. The A is HI, isn't it? That's the reactant. So the reactant number 5 is HI. So if it's second order,
The rate law would be this. Right? Because we're talking about the reactant, the second order.
And the answer there is, if the second order is proportional to the inverse, right?
So 1 over HI.
Would be proportionality versus time. How about number 6? Yep, that's running out of juice. Yeah, find another one. Here's one. Is this the one I wanted? Yes. So we got a slow step. Got step 1 and step 2. What am I starting to describe here? Mechanism. The mechanism has elementary steps, at least 2. This would be the overall reaction. Well, I didn't write it there. The overall reaction. Oh, they give us the overall reaction.
2A sub 2 plus B sub 2 equals 2C. So this one is very slow, and this one's just slow. So this is A2 plus B2 equals R plus C, and just plain slow step is plus R equals C.
Okay, that's the proposed mechanism in 2 elementary steps. So which one determines the rate of this experiment? First or the second step? Determines the rate. The rate is always determined by the slowest step. Right? It can't go any faster than this one. Right? If you have 2 people on a bicycle built for 2. Now that's not a good example, because that would work one person. You could go a little faster with just one person doing all the work. Let's say you got a bucket brigade trying to put out a fire. How fast can you transfer water to that fire? No faster than the slowest person in that chain. It's going to pile up at some person. If you're not all going at the same rate, one person's going to slow it down. They determine the overall rate for the reaction. Okay. Does this one satisfy conditions? Let's just use it as a teaching moment. What's the first condition? When you add those 2 together, it has to equal the overall reaction, doesn't it? So let's see if it does. Okay, there's A2 and A2. So we have 2 A2s, right? That one, that one. We have a B2. We have an R. This is on the reactant side. Then we add these together. We've got an R, and we have 2 C's, right? Okay, it's overall reaction. Now you can cancel the things that are the same on both sides. So the R is gone. And that's it. So 2A2, B2, 2C. So it satisfies that condition. Let's see. Oh, here's a good one. We get our basic concepts out of the way before we start chugging through calculations. How about 8 and 9? 8 and 9 refer to this graph. So this is reaction progress. It could be based on time, it could be based on product production, whatever. They never do put any units on that one. But this one is the energy of all the components in the reaction. So if we start off here with reactants, and we're going to end up over here with products. Okay, so the first thing you can see from this is you've added energy to the reactants, ended up with products. Is this an exothermic or endothermic reaction? Yep. You put energy in, but you didn't get it all back. Right, it's endothermic. Okay, so here's the possible progress for the reaction. The energy is going to go up and then come back down. Okay, so we're adding energy to the reactants to get the reaction to go. And suppose we want to measure from here to here. What's that called? You can use a whole name or the abbreviation. The amount of energy required to get a reaction to start is the activation energy. Okay, ease of A. What if we go from there, and we say from here to here? What is that? That's the enthalpy of the reaction. Yeah, I can use abbreviations. The enthalpy of the reaction. And since the sign convention is if energy goes in more than it comes out, the sign's going to be positive, right? Because it's all reference to the system. We put energy into the system, but we don't get a lot back. So that's positive. We've added to the system. So the positive enthalpy means we have an endothermic reaction. Okay. Let's see, what are some other significant? What if I say we're going to introduce a catalyst to this reaction? What will the curve look like then? Will it be, we're going to end up, right, with a catalyst, you start off with the same reactants, end up with the same products, right? Catalyst doesn't change that. What does a catalyst do? Go faster, yes. Now, this energy diagram will show us why it goes faster. It goes up. It doesn't have to go as high. It doesn't need as much energy. So this one is a catalyst. So that's why it goes faster, because with less energy required for the reaction to proceed, more of the molecules have sufficient energy. Now, the key to this is by using a catalyst, we don't run the reaction on the same mechanism, right? The elementary steps of a catalyzed reaction are different than the elementary steps for an uncatalyzed reaction. The catalyzed reaction will run faster because the slowest elementary step in the catalyzed is faster than the slowest elementary step in the uncatalyzed. Simply because the catalyst is involved.
and it reduces the amount of energy required to get past that particular elementary step.
Basically like a battery for the extra.
Sort of. I wouldn't carry that analogy too far. Because the battery analogy says you're adding more energy, but you're not. Right? At the same temperature, you need less energy. So more of the molecules have sufficient energy for the reaction to go. This is an energy distribution. This is the number of molecules. Right? So uncatalyzed, well, actually, this is the energy distribution either way, doesn't matter. Like that. Right? So these, no, I got that backwards, excuse me. This is the number of molecules. This is the energy of the molecule. So, the number of molecules, they hover around this much energy. But you're going to have some out here that are higher energy and some here that are lower energy. So, with an uncatalyzed reaction, it takes this much energy. So, all of these will react. But with a catalyzed reaction, it takes less energy to go. So anything above that point, plus those, is the energy of the catalyzed reaction. So with the same energy distribution, if a catalyst is introduced, more of them react because you're making a lower energy, reactants at lower energy will react. Whereas without the catalyst, you need that much higher energy to make them react. So we haven't changed the energy distribution at all. We just changed the pathway by which they reach the products. And that allows lesser energy molecules to react. Okay. Let's see. Oh, okay. Let me go ahead to this one. Can I erase that now?
Yeah.
Okay.
Make sure to hit record this time, right?
Yes, it's recording. Thank you.
Last time.
Give me a heart attack.
All over.
Yeah, so I stayed in here for another hour and a half and finished. Just recorded the whole thing over again. It's on Blackboard. Actually, I mean, it was a pain, but with that practice session, I think I did it better the second time.
Make sure to save it in case you ever, that happens again for.
Oh, yeah.
semesters, you know what I mean?
Right. Okay, how about this reaction? If we have H2O2 yields 2H2O plus O2. That's a common reaction. The hydrogen peroxide on your shelf will eventually react to produce water and oxygen, just sitting in the bottle. So over time, it loses its strength because this deteriorates it. It makes more of that. Now it's useless. But we can make that reaction go a whole lot faster. And I've seen it done. It's a joy to behold. If we take these elementary steps, see, this is the uncatalyzed overall reaction. But we're going to introduce a catalyst, the iodide ion, as potassium iodide. And when we do that, this mechanism comes into play. Step one, we take one of those molecules, combine it with iodine, that yields water plus the oxyiodine anion. Let's see if that balances. 2 oxygens, 1, 2 oxygens, 2 hydrogens, 1 iodine. Okay, so that one balances. And then we take the other one, right, because we got 2, and we combine it with this thing. And that completes the reaction. Oops, not hydrogen. Oxygen. Plus the iodine ion. Okay, that's the proposed 2-step reaction mechanism for this catalyzed reaction. Now, if you're just given that, and I don't add all that commentary on catalysts, can you find out what the catalyst is in this reaction? Well, think of the definition of a catalyst. It goes into the reaction, it comes out of the reaction without being changed at all. Right? So, iodine goes in this side, comes out that side. That's the catalyst. Okay? It's tempting to say, oh, there's a catalyst right there. But it was created in the reaction and consumed in the reaction. You don't even know it's there. Right? So it's not the catalyst. It's an intermediary. It's an intermediate product, intermediate reactant. The catalyst is the one you put in and it comes out unchanged. Okay? I had a student from Logan. Did I tell you this story? His wife was pregnant, and they went, got the ultrasound and found out what the sex would be. So during the reveal party, he bought some over the internet, some 30%, 30% hydrogen peroxide. Normally what you get on the drugstore shelf is 3%, but this works better with a higher percentage. So he got 30%, and he bought some potassium iodide that provided the iodine ion. And they added a little bit of dish soap to make it suds, plus color. So the blue color for if it was a boy, the red color which would make pink if it was a girl. So he put the color in, put the soap, a few drops of soap in, he put it in a 2-liter bottle, right? So it would come out and squirt really high. And all you had to do was just take the potassium iodide crystals and go dump them in, and the reaction was immediate. And it just went, make this, I think it was blue foam, come shooting out the top. So they revealed the gender of the child. Okay. So, I didn't put any phases up here. This is a liquid. This is a liquid. This is a gas. The iodine is aqueous. Actually, this is not a liquid because it's not pure. It's aqueous. There you go. This is liquid, and that's gas. So is this a homogeneous or a heterogeneous catalyst?
Homogeneous?
Yes, it's in the same phase as the reactant. So it's homogeneous, right? Okay, let's see what else we can do here. 1:45. Start the lab at 4. If we could get out of here by 3, that would give us enough time to do some preliminary
discussion and talk about the calculations. Oh, we can do those in here too. How about you remember the collision theory? What are the premises for the collision theory of chemical kinetics? Let's just review those. Number one, molecules must collide to react. Where the theory gets its name. Minimum amount of energy to react. In other words, they have to collide, but they also have to collide with minimum amount of energy before they react. That's the activation energy. Okay, and number three. Must be properly oriented to react. In other words, if the reaction sites for the step of the reaction of the mechanism, reaction sites are on near my little fingers and my thumbs come together, doesn't matter how much energy there is, there's no reaction. Orientation is critical. They have to collide, they have to have a minimum amount of energy, and they have to be oriented properly to react. That's the collision theory in a nutshell.
I actually heard a good analogy for was talking about like Velcro. Like he's talking about picking up together. If you have two sides of Velcro that don't go together, you can try to put them together all day and they don't do nothing. But
Yeah.
turn them around, put them on the right side.
Uh-huh.
That's how I remember it when I was doing one.
Okay. All right. Okay. So where was I going with that? If we have this reaction, this is number 13, by the way. This reaction overall, this looks familiar. I think we've seen that one before. And the very slow, yeah, we have seen this one. So step one is this one, plus B2 yields RC, and step 2 is A2 plus RC. Okay. And this is the very slow, and this is the slow. So we already determined this is the rate determining step. According to the collision theory, the activated complex that forms in step 1, okay, so we're focusing on this one, could have which of the following structures? Remember when, I think it was on one of the slides, at the top of the, it was an animation. The top of the curve, the energy curve, you have a collection of atoms which are derived from the reactants. And they're nothing but dotted lines connecting them. So that was the activated complex. Those dotted lines represent bonds that are being formed or being broken, either one. So the activated complex would be derived from which one of those steps to determine the rate? It has to be from the first one, wouldn't it? That's the very slow one. So what do we have here? Well, we've got this A2, coming together with this B2. So how would this complex be activated? Let me see. Oh, that's not very. One second. Not bleeding through to the other side. No, those lines are not showing very well. Right. So as these two come together, the activated complex, as these two come together, start to break bonds, form bonds. Should we, process of elimination, should we have any R in here or any C in there? No, because we don't have any products yet, right? These are the products of that elementary step. So it's based on these two only. So as they come together, these bonds start to break. And new bonds start to form. Right? So this is the activated complex for that step. Now, once they form, they get new identifications. Right? It doesn't just come out AB, because that doesn't give us any reaction. It has to come out as RC. That's not a very good example. That's the trouble with using substitutions instead of real atoms. Okay. So, I'm going to switch this over a little bit. The only reason I had it that way is so I could pick up the periodic table, but I don't think we're going to need it as much today. So we'll give us a little more space over here. Because what I want to do is number 15, I think. Let me see how involved that is. It's okay, one page. All right. So if we have this set of data, you got time? Yeah. I'm gonna give it a shot. So what is that anyway? Se is selenium, right? It's in the same family as sulfur. So SO4 would be sulfate, SO3 would be sulfite. So SeO3 would be selenite. Sulfite, selenite. So ites become us's in acids. So this is selenous acid.
And then concentration of acid at the beginning, concentration of iodine at the beginning, and rate in mole per liter per second. Okay.
So if we label these 1, 2, 3, 4, 5, 6, 7. There's 1, 2, 3, 4, 5, 6, 7. We put in the information.
10 to the minus 4, 10 to the minus 2, 10 to the minus 2, and this happens at a rate of 66 times 10 to the minus 7. This one, these are all 10 to the minus 4 down here. These are all 10 to the minus 2. And this happens at a little faster rate, about double. This one, faster still. And 4, we're going to take this one back down. So these are a series of experiments. To determine that rate, you have to conduct this experiment at those concentrations, initial concentrations, each time to get each one of these rates. This is initial rates experiment. These values are determined at the very beginning of the reaction, then you don't care what happens afterwards. 1, 4, 2. And this one happens at 6.66 times 10 plus 7. 5 is, hold this one, same as the one above it. Take this one down a notch, 2 or 4. 2. This one happens at this rate. Now notice that this is not scientific notation. But the reason it's done that way is so that we can hold this value, the exponent, constant. I'm going to kick this one up a little bit. Okay, and the last one. Well, just do the theory. Because that one's scientific and this one isn't. Okay. No biggie. So we want to find out what the rate constant is. The first thing you need to know is what is the rate law governing this reaction. Okay? So the rate law is this one, well, the rate constant, then the selenous acid to the, let's see, what do we use? NMP. I want to be consistent. N, M, and then P. This thing's crapping out on me. Let's see if this one's back in business. Right, so we need to find out this and those. But this is the question that's being asked. What is that K? All right. So we want to find out, first of all, let's try to find out what this one is. So in order to find out what this one is, we need to find two experiments in which the concentration of hydrogen and iodine do not change. They're held constant. Here's a good example. We could do that one. We could do this one, or we could do that one. But what we're going to do is we're going to ratio. It's best for the calculations to find the rates that are farthest apart when you start ratioing these. So if we have these two held constant, then it's better to do 3 and 1. And we're going to put 3 over 1 because we don't want a fraction. We want a number greater than 1. So first calculation, we do rate for experiment 3 divided by the rate for experiment 1. So what does that equal to? Well, it's equal to K in both cases, right? K is a constant, it doesn't change. Right? So K, and then this one for rate 3, which is 1 times 10 minus 4. Is that right? No, 3, excuse me. 3 times 10 to the minus 4. So 3 times 10 to the minus 4 is this one to the n power. And then rate 1 is 1 times 10 to the minus 4 to the same power. Because we're using this law. Well, what's the rate 3 and what's the rate 4? Well, the rate 3 is 4.99 times 10 to the minus 7. And it doesn't matter, you don't have to put the units in there because they're going to cancel, right? We're ratioing this stuff. So the units don't matter. And 1 is 1.66 times 10 to the minus 7. See if we're picking that up. Yes. Okay, how about these? We just said that we're going to hold these constant. So do the same thing for both experiments, aren't they? So if we put values in for this one and this one, they cancel because they're equal. So it doesn't matter what their powers are, they still cancel. So now what do we get? The K's cancel because they're equal to one another. Now what we get is 3. We don't get anything until we get a new marker. 3.00 times 10 to the minus 4 to the n power divided by 1 times 10 to the minus 4 to the n power equals that one divided by that one, which is what? Well, we just need to do a calculation. Stop me if you have questions. So I get 3.006. This ratio here. Okay. So what is this expression? If you've got a number to a power divided by a number to a power, that's the same thing as this number divided by this number to the power. Oops. To the power, isn't it? Are we good? Okay. So 1 into 3 is 3, and 10 to the minus 4 cancels. So that's 3 to the n equals 3, roughly. So n is equal to 1. Okay, so now we know that N equals 1. And if we do the same thing with the hydrogens, we want to hold the selenous acid and the iodide constant. So let's see, where are they the same? Selenous acid, 7 and 6 might work.
Is that the one I used in the example? Yeah, 7 and 6.
So if we compare, first we compare this one and this one. Now if we compare this one, ratio that one to that one, then these terms drop out and leave us with this one. So what we're going to end up with is 7 and 6, 7 hydrogen, 4 divided by 2, right? 4 divided by 2 equals 5.33 divided by, no, let's change this to minus 7. 53.3 times 10 to the minus 7. So 53 divided by 13.4. What is that? 3, 4, maybe 4? Yeah, roughly 4. Oh, and this is to m. So this is 2 to the m power equals 4. So m is equal to 2 for hydrogen. Did everybody see the steps that I skipped? I was comparing, using the same procedure, I was comparing 7 and 6 because these two are held constant, right? And we just let that one vary. Okay? And if I follow the same steps here, that leaves this one in the middle, these all cancel, and just has experiment 7, experiment 6, which is this one and this one, and then concentration 7 and 6 of these two to the power. Okay? So the last one we have to do is where we hold these two constant and let this one vary. So if we use this experiment here, we're going to let that one vary and hold these constant. So 6 against 1. 6 against 1. And using that logic, we get 4 divided by 2 again. See, 4 divided by 2 here to the p power. And then the rates, 13.4 and 1.6. 6. So that gives us, what's that, about 8? Becomes 4 and 8. Yeah, that's about 8. So 2 to the what power equals 8. P equals 3. So now we have our powers, our orders, and all you have to do now is that you got the order is pick one of these experiments. I think my example, I picked experiment 4, and you plug in the values for iodine, hydrogen, selenous acid, go in here to these powers. And they're equal to the rate. They're equal to this rate. And then K is your unknown, and you solve for K. All right? I know it's a lot of work. So I probably wouldn't give you one that has to go through the entire set like that. I would just set it up and do a lot of the preliminary work and then ask a question about it. But if we do that, then K turns out to be 5.2 times 10 to the 5th. And that's an example of method of initial rates. I'm tired. Okay, how are we doing on time? Good. Let's see what else we can come up with. What about this one? I'm going to erase all this stuff. Okay. And make room for the next one. I'm not going to erase that because we might need it. Okay. Oh, the other good thing about this review document is it will show you useful information on the last pages. So these last pages, that stuff will be on the test. You won't have to memorize all this stuff that's on the review document, just like last semester. Let's see, where was I? Here we go. Let's see. If I give you this reaction, hydrogen peroxide and iodide and acid, and we get triiodide ion, 2 waters. Okay. First of all, what's the general rate law for this reaction? We just want the reactants, right? So we would want the concentration of this, of course, with our K. N, and then I. Can I use the coefficients for anything? Trick question. No. Coefficients in a balanced reaction cannot be used in the rate expression. These powers and that rate constant have to be determined empirically. And then we have hydrogen. There we go. This is N, M, and P. Okay. So if I tell you this reaction is first order in hydrogen peroxide. What goes up here? A 1. But we don't have to write the 1. Right? It's automatically 1. The only time you have to write 1 up here is if it's a 0, 2, or beyond. But okay, we'll do it just for argument's sake. And if I tell you the reaction is second order in this one, what is M? Second order in iodine, it's a 2. Right? You know, if I tell you it's 0 order in hydrogen, like that. But is that the way you write the reaction? The rate law? No. Rate would be reduced to these terms. Yeah, we'll do that just for argument's sake. Here. And leave the hydrogen out. The hydrogen has no bearing on the rate law because it's 0 order, and anything to the 0 power is 1. It just disappears. Okay? What's the overall order for this reaction? One plus 2 plus 0. 3. Reaction order equals 3. Okay. Okay, here's a good one. Let's say here's the rate expression for a reaction. Okay, so it's first order in A, second order in B, overall order is 3. If we take the concentration of B and we increase it from 0.1 molar to 0.4 molar, what effect will that have on the rate? This constant doesn't change. These values don't change. And we're holding A constant. We're only going to change B. So B goes from 0.1 to 0.4. What effect does that have on the rate? How much have we changed B? 4 times. Right? 4 times. Squared means 16 times the rate. That's what that means. The effect on the rate is squared for a change in concentration of that factor. Okay? If we did the same thing for this one, it would simply increase the rate by 4 because it's to the first power. What if we went from this one to this one for A and this one for B? What effect would that have on the overall rate? Well, you would still have this 16 times for B, but you would only have double for A. So 2 times 16 is 32. So the rate under those conditions would increase 32 times. Okay? Does that spin anybody's head around? Before I jump on a different problem. Question? Make sense? Okay. Oh, before I forget, Megan, you got some homework to turn in.
Yeah, I'm still working on it.
Okay. Just want to be sure that
It'll
you.
be turned in tonight.
Just want to be sure you haven't got stuck with some technical difficulty that I can fix.
No, it's just I've been all over the place lately, so I've had some time, but I haven't had a lot of time either, so I'm just trying to work on it as I
Okay,
when I had the time, but it'll be turned in tonight.
okay, good deal. Let's see.
Suppose you have mechanisms proposed for a reaction, and one of them is unimolecular, one is bimolecular, and it really doesn't matter what order they occur in. Bimolecular. Molecular. And termolecular.
And what you know about probabilities and the contributions that they would make,
These are all elementary steps in a mechanism.
which one's the rate determining step?
I'm gonna guess the termolecular.
Yeah, it's the least probable, therefore the slowest. You remember why? It's simply the probability of bringing three molecules together with the right energy and the right orientation to react. The probability just goes, well, actually, it's like, goes down to almost nothing. So that means it's going to be very slow. Right. That's the one that would determine the rate in your proposed mechanism. That's why most chemists that work in this line shy away from termoleculars wherever they can. Because they really, and if you know the overall, of course, you're going to know the overall rate equation for your reaction before you propose these steps. So unless your reaction is extremely slow, you're not going to go for a termolecular step. You know, if it's a reaction that takes years to detect, yeah, maybe a termolecular might fit in there somewhere. But if it's one that takes seconds or minutes, there's no way a termolecular would fit in that scenario. If you were trying to write one of those for a dissertation, your advisor would tank that one immediately. He said, you don't want to go before your committee with that nonsense. Okay. Oh, one thing we didn't talk about. When we had our reaction curve, went like this and like that, okay? So if this is reactants, this is products, and this is uncatalyzed, then we decided that our activation energy was here, right? What if you're starting from this side with products as reactants, and now you're going to head for this side as products? What's your activation energy now? It's just that much. Okay. So most reactions are able to go backwards. It's just they might not go as fast as they did forwards. This one probably will go faster this direction than that direction, because it's harder to get that much energy to make a reaction go this way. And when you're on the other side, as long as your temperature is constant, you've got more energy available here. So you're probably going to prefer this side. But that's for a later discussion. Okay, how about this one?
This is a tricky one. It's always spins students' heads around. Let's say we have here, time, and we have the natural log of our reactant. And we do like this, right? Plotting A against time and natural log against time should be a straight line. If it's a straight line, it'll be a negative slope, right? So what if we have, you're given the equation for that line, y equals mx plus b, so m, let's say m is negative 3x plus, I don't know. Let's say it's a negative. Negative 5 times 10 to the minus 6. Right, so there's y equals mx plus b. First of all, what's the order of this reaction with respect to A? So if we were to write the rate law, what would be up here? Well, if it's a straight line and it's a log, right? First order, right? So that would just be 1. That tells you with a straight line that this is log A against T gives you a straight line. That means that it's first order with respect to A. Okay. What's the value of the rate constant? Well, if we're plotting y equals mx plus b, the k is the negative of the slope. So if the slope is negative 3, k is equal to 3, isn't it? Okay. Now what would be our starting concentration? You want the y-intercept, don't you? Because that's when time is 0. So this is going to be log A 0. So you just set this one equal to that one, which is negative 5 times 10 to the minus 6. And you do the anti-log of that number. So everybody remembers on your calculator how to do the anti-log. The anti-log of the common log, right, is this number, let's see, no, this number to that power, 10 to the x equals A. This one, you just change the base. So this is e to the x equals A. Okay? So you say e, e to the negative 5 times 10 to the minus 6. Let's just see what that is. I'm curious. Negative 5 exponent 6. And I do e to the x. So that would be starting concentration would have been 0.9999, rounded off to 1. So we would have started off at 1 molar with that equation. Okay? That doesn't mean you have to start off at 1 molar. It's just that under these conditions, you could actually start off anywhere on that line, and this equation will still hold to give you whatever you're solving for, actually. So that's an exercise in how to read a graph. I mean, this is generic here. This has got hard numbers to it to see if you really know what those numbers mean. All right? Let's see.
What about this one?
Let's use half-lives. See if we can find out something about this reaction. So let's say we have A is making products. Okay? And we're given the initial concentration of A, okay, concentration of A at time. So initial concentration of A is 6.4 molar. That's where we're starting. The first half-life is 60 minutes. Yeah, 60 minutes is the first half-life. So what does that mean? After 60 minutes, half of that's gone. 3.2 molar. The second half-life is only 30 minutes. So after another 30 minutes, half again is gone. 1 point, wait a minute, what am I doing? Yeah, 1.6 mole, right? Half of that. So that time period is at 90 minutes from the beginning. Okay. So if you're told that the, the order is 0, what does that mean? The order of A is 0 in this reaction. Rate equals K times A to the 0 power. And the half-life, if that's 0, the half-life is this, right? 0 order. Half-life is A0 over 2K. So, what would K be? Do we have enough information to do K? I think so. Let's see, we know what the initial concentration is, and we know what the half-life is to take it to the next level. Right? So if we're starting at 6.4 and we want the half-life from that position, that's 60 minutes, isn't it? So the half-life then is 60 minutes. The initial concentration is 6.4 divided by 2 times K. And there you have an equation in one unknown you can solve for K. So what would that be? 120 divided by 6.4. Now that would be 1 over K. So K is equal to 6.4 divided by 120. Yep. Let's see what it is. .33 times 10 to the minus 2. Now it has units, but I don't care about units right now. I just wanted to do the calculation. With that information, you can determine what K is, because not only are we given the half-life and initial concentration, we're told that it's 0 order. Now, if we're not told if it's 0 order, can we determine if it's 0 order? We did that on some of our slides, remember? We took the data and we said, okay, if this is the case, then we should be able to get K to be the same if we use this as our starting point or this is our starting point. So we just do those two calculations. This one's A0 or this one's A0 for different half-lives and see if the K's agree. If they don't agree, that one's out. Right, that would be more complicated, but it could be done. Let's see. We're doing on time. 20 minutes to 3. Huh?
It's about 2:40.
Yeah. You need a break.
I need to go break.
Yeah. Let's take a short break.
Julian, how do you study for your test? Not efficiently, apparently. Are you doing that? It's just the little things I'm getting confused on. I don't do that. I mean, I'm not doing as great as I want to, but.
Yeah, I'm not even, no, my tests are bad. Like, he done told me that, like, I have time, to get.
Are you saying Charlie?
Who?
Not in the past hour and a half. She was in her office, or
Yeah.
her old office.
Yeah, that's what we're ranking on. I can
Yep.
roll about 200, 250.
Okay. Here's one that we haven't talked about yet. We've talked about activation energy, but we haven't talked about calculations using activation energy. So the Arrhenius equation is a little hard to use, but the integrated version of the Arrhenius equation works a whole lot better for things like this. Say we have we have this reaction. And that yields this one plus this one. And the rate constant for this one has been measured empirically at 1.08 times 10 to the 7th. See, I might as well put the units in here. everybody understand what I mean by this? The -1 power? Okay. And this is at 298 K. So if you're going to use the Arrhenius equation, you've got to conduct the experiment at least 2 different temperatures. Because the rate constant won't change unless you change the temperature. Constant. Oh, and the activation energy is given. This is equal to 11.4 kilojoules per mole over the range of 195 to 304 K. So we're absolutely certain that the activation energy is this value over that range. So what does that mean? That means that the activation energy doesn't change with temperature. Well, it can, but we've verified that within that range, activation energy is constant. So the only thing that changes is the temperature if we conduct another experiment at a different temperature. And that's what we're going to do. Except we want to find out what the rate constant is. So this is the first one, this is the second one. We don't know what that one is, but we do know the temperature, 233 K. So you need the integrated version of the Arrhenius equation. And if you look at the let's see, useful information, it should be given. Here it is. Here we go. So here's the Arrhenius equation. Yeah, I just want to be sure this is it. Natural log of K2 over K1, the activation energy over R, and then the 2 temperatures. Okay? So what do we know? Well, we know K1. We don't know this one. That's the one we're solving for. We're given this one. Okay? R is given as 8.3145 joules per mole K. Okay, so that's R. And the temperatures are given. The temperatures need to be in K, as always. So we're given that one, they're given that one. So really, all this problem requires is that you plug in the values and solve for the unknown, which is this one. So that might give you a little trouble, trying to solve a log equation like that. Let's see if we can do it. So how does this work? The natural log, K2, which is unknown, and then K1 is known, 1.08 times 10 to the minus 7. I'm going to leave the units out because if we do this right, the units come out right. Activation energy is 11.4, and then 8.3145, and then 1 over the initial temperature is 298 minus 233, 1 over 2. Okay. There's our equation. Things are crapping out on me. Okay. So let's resolve this side first. The inverse is 198 minus the inverse of 233. 298 inverse, and then 233. this term right here is minus 9.36 times 10 to the minus 4. And this term is 8.3. This is 1.371. Okay? Now, what do we do with this one? We've got a log of a quotient. Remember your log rules. The log of a quotient is the same as the log of the numerator minus the log of the denominator. That's probably where most students would stumble, remembering that relationship. So if we say the log of K2 is equal to what? Well, let's take the log of this value, 1.08 times 10 to the minus 7. And take the natural log of it. That's minus 16.04. But minus here is times the minus here is plus. But then when we take it on that side, it becomes minus again. So it's still minus 1.60. No, not 1.16 times 0.41. And then this term here so that one. Yeah. I'll just punch them in again. 1.371. 9.36 times. Okay. So this one, and this term is a minus 1.283 times 10 to the minus 3. We take that one, subtract from this one, so it's basically that number. Actually, we add that one to this one, and it's still a negative. Yeah, 16.04. Okay, so that's K2. So now we just need to do the anti-log of that number. Oops. So the anti-log of that number is the power of E. And I get 1.08 times 10 to the minus 7. Now let's see if that jives with this answer. I did something wrong. K1 is this. K2 is unknown. 11.4. Ah. Made a really stupid error. Any idea what it was? See the units here? Joules per mole K. Activation energy has to be in joules. $11,400. Okay. So, with that correction, This is still true. This one has to be recalculated. So that's 1.37 times 10 to the third. There we go. Let's see. This is still good. So that comes over here. This one changes. Okay. So now this one times that one would still be the negative. This is 1.283. And 16.041. I did something wrong. Hold on a second. This is minus 17.3. Then that becomes the exponent of e. I get 3.3. 4 times 10 to the 7th. It still doesn't look right.
It's off.
Okay. That one, that one. Ah. Okay. K2 is this one. I think I got my values turned around. See how easy it is to mess up these things? I'm not even under pressure. Here we go. So is this K2 temperature, K2 there, 1 here. This is K1. 1 and 2. This is the first temperature, this is the second temperature. This is the first K value, this is the second K value. This one minus that one. This one times 1 point. Let me see if I did that calculation correct. And 3, 6, 10 minus 40. That's right. This is right. That should be right. K2. Then 1.08 exponent. 7 sine natural log minus 16. So this is minus 16.04. Minus minus is a plus. Comes over here is a minus. And this one times this one. Minus 1, 2, 8, 3. 17.3. And then, oh. Yep. I must have hit the wrong button. Well, still didn't give me the right answer. This should be negative. Oh. Well, I have to work on that one. I don't know what to say. Difficult. Anybody else try this one? Watch me mess up. I think it has to do with which one's 1 and which one's 2. If we're given this one as 1, what would it be? Actually, 1 should be the lower temperature. That's it. 1 should be the lower temperature. 2 should be the higher temperature. So that means this should be negative, that should be positive. And this one should be on top. So those should be reversed in solving. That's the way it should be. So whenever you encounter a problem like this, the lower temperature should be T1, the higher temperature should be T2. And everything else will fall into place from there. What time is it? It's after 3? Okay. I think it's time to talk about, talk about our lab. And if I do it in here, we can keep recording. That way, all this discussion will be on the video. So let's say this is chemical kinetics lab. My markers are starting to crap out of me. Okay. So let me pull these things out. Tell you what. I got one of these already. Pull one of these. One of these. All right, for the kinetics lab, pre-lab questions. Let's look at the pre-lab questions. They might give us a better start into what we're going to deal with in the lab. Household bleach has 5% sodium hypochlorite. So this is pre-lab. Number 1. Okay. If your household container has 5% sodium hypochlorite, if you look at any of the bottles of bleach, years ago, they used to be 5.25%. Now, most bleach that you buy is the ultra bleach. That's at 6%. 6% is what we're going to be using in the lab. So you use the same procedure for answering this question, only substitute 6%, and you can calculate the molarity of the solution. So first of all, what does 5% mean? Well, Prelab question says by weight, right? So that means 5, well, I gave decimal points. We have 2 of these. 5 grams of sodium hypochlorite per 100 grams of bleach. That's what that means. 5 parts per 100. Weight. This means that's weight and that's weight. Okay? So, calculate the molarity. All right. So the molarity of this one, it's going to be a series of conversions. First, we want to find out how many grams of sodium hypochlorite per liter of bleach. Then we can convert the grams to moles because we know the formula. To do that, we need grams of bleach per 1 milliliter of bleach. That doesn't help us much. Well, except for grams of bleach, so that cancels, right? But that gives us grams of sodium hypochlorite per milliliter of bleach. We need per liter in order to talk about molarity. Right? So we need milliliters here, cancel these milliliters, liters on the bottom. So this is 1,000 milliliters per liter. So there we go, and there we go. So now we have grams per liter. We just need to convert sodium hypochlorite to moles. So grams on the bottom and moles on the top because grams cancels and leaves us with moles. So what's the molar mass of sodium hypochlorite? Sodium is 2300. Oxygen is 16. And chlorine is 35, 45. 5, 4, 14, 7, I think. 3, 4, 5, 6. Carry the 1. Yep. Grams per mole. 74.45. Okay. So that will give us molarity of 5% bleach. Why do we need to know that? Because of this. That's assuming you're going to do blue. You don't have to. Right? We need to know the concentration of bleach in order to find the order of the bleach, because we're going to use bleach in 2 different concentrations. We're not going to use it at full strength, right? If we use it at full strength, you'd add the bleach, and then before you could take your first measurement, it'd all be gone. So we're going to dilute it. Okay, so the calculation then is 5 times 1.08 times 1,000 divided by 100 divided by 74.45. So I get 0.725 molar bleach.
Okay. That's Prelab question 1.
So do we just do the same thing again for question 2?
Let's see, question 2. What is question 2?
Grams.
How many grams per liter of sodium chloride are required in order to prepare a, yes, you want the same molarity of sodium chloride as the bleach. Why? Because after we use the bleach at a certain concentration, you're going to replace some of the solvent with sodium chloride solution to maintain the ionic strength of the solution. You don't want to dilute it with water because that will change the way it behaves in solution. So we're going to dilute it with the same concentration of sodium chloride. Now, of course, it's going to be different than that because we're going to use 6%. Right? So let's do a 6% calculation. What if we
For
just,
question 2?
I'm sorry?
For question 2?
Well, no, question 2 would actually be using this.
I
So,
was gonna say, isn't it the same thing, just minus the 1 mole over 74.45? Would that be our calculation?
yeah, that would work.
Because
No, because 5% sodium chloride won't be the same molarity as 5% sodium hypochlorite. But you need to start from here. So we need 0.725 molar sodium chloride. And let's see, question was, how many grams per liter of sodium chloride are required? So this is the molarity, or moles per liter. We want to find out how many grams per liter, right? Okay, so all we have to do now is just convert moles to grams of sodium chloride. Okay, so sodium chloride would be 23 plus 35.45. You just take the 16 out. Eight, 6, 5. I think that's right.
It's 58.45.
58.45.
So in the bottom of that one, is that 1 liter over underneath 0.725?
Yes. So that gives us grams per liter. So that's how many grams of sodium chloride you need in 1 liter to make the same molarity as 5% sodium hypochlorite.
So the answer is 42.376.
38 grams.
We just rounded up because I did 42.4.
That should work. Oh, yeah, because this is only 3 significant figures. Yeah, you're right. Now, for actually doing the experiment, you would start with 6% here, and you would get a value there, and then you would take that value here and calculate a different sodium chloride. But I've already made up that solution, so it doesn't matter.
And then on number 3, it's basically the same thing as number 1, except we're using 0.800, or is the same as question 2?
It's the same as 1 working backwards. Because with 0.8 molar sodium hypochlorite, okay, let's do it. It's just dimensional analysis. 0.8 moles per liter, and this is sodium hypochlorite. And the question is, what is the percent? So we're going from here backwards to there. So if we know this is our molarity,
then we want to convert this to grams. And it'd be the same number here, 7445. That would cancel moles. Gives us grams per liter. And then the grams per liter needs to be in milliliters. So we would say liters here, milliliters there. Right? Gets rid of liters, milliliters. Now we can use our density, which was 1.09, wasn't it?
Yeah, 1.09.
So milliliters on top and grams on the bottom for a density 1.09. So this is grams of bleach. And this is grams of sodium hypochlorite. And then we want to multiply by 100 for percent. So I get 5.46%.
What?
Is that what you got?
At 5.50.
50? Oh, round it off. Yeah, sure. Oh, on that handout, I did do it for 6%. You see this one right here? The part 2, I went ahead and showed you 6% sodium hypochlorite. And that, with 6%, the equivalent molarity is 0.878, was it? Yeah, 878 molar. So that's the molarity of the 6% bleach. And that would be used here to find out how many grams of sodium chloride to make in a liter to give you that same molarity. But I've got bottles of this stuff made up already. You don't have to do that. All right. So, in the process of doing this experiment, you're going to find out, you're going to test how much bleach is required to bleach the color out in a certain amount of time. I'm trying to think, how much time did they give us?
3 minutes.
3 minutes, okay. So you need to bleach it out in 3 minutes. And once you find out how many drops that is, add it to your vial of blue color. You need to find out what concentration of bleach does that represent. Okay, so in order to do that, you need to know what's the volume of a drop, right? So you could do, there's several ways you could handle that. You could say, all right, so I put, say 20 drops in there. So you take 20 drops into a volumetric and you measure what the volume is. That's kind of sloppy. It would be better to use this density here, 1.09 grams per mil, and measure out just any convenient amount, say 50 drops. Right? So 50 drops equals a certain mass. So 50 drops equals this mass. 50 drops per a certain mass. Then you use the density, because we already know the density is 1.09 for that one. And that's grams, 1.09 milliliters. I actually want to, really ought to flip it. Let's do it this way. So it's this much mass per 50 drops. And then we know that it's 1.09 grams per milliliter, right? So the grams cancel, whatever they happen to be, and that leaves us so many mils per drop. So now that you know how many milliliters is each drop, then you say, how many drops did I use? Well, then I multiply that times this, and that gives you what volume of bleach did you actually add to your container. And your container is going to be a certain volume, and its total volume then is going to be plus that volume. Okay, so the total volume then, you'll know with how many drops you added at this concentration, you'll be able to tell how many moles of sodium hypochlorite you added. And then you'll know the moles of sodium hypochlorite per volume in the cuvette. And that's how you calculate the molarity that's actually in the reaction vessel. Okay? So once you know that concentration at full strength, you just cut the number of drops in half, make up the difference with sodium chloride by volume drops. And we have to assume that the drops are the same size. So it's kind of sloppy there. But then the second experiment, when you run at half concentration bleach, will just be that value divided by 2. Okay? Then you'll have 2 experiments run on this same kinetics. And remember we said that if rate equals some K value times the blue color and bleach, okay, and we'll combine these two into a pseudo constant. Okay, now we can plot this against time for 0 order, natural log of that against time for first order, and reciprocal of that against time for second order. And look at those curves. That's what I did on this Excel spreadsheet. I did those transformations in Excel, did the plots, and found out which one was the linear plot. And once you know the linear plot, then you have that value. Is it a 0, 1, or 2? Okay. Now that you know that's a 1, or a 2, or a 0, whatever, then you can use, once you find out what this is, and we'll have to talk about that too, then you can determine, based on the rate is equal to that times that, to this power, then you can do it again for the different concentration. And this is going to be K prime 2 will be different. All right, so you would have a ratio of those two. And I think I've got another, here it is, calculations. And I'm using blue for this one. That's good, that's convenient. So we might as well stick with blue. Let's see. Okay, this says it's first order kinetic for blue.
You got to prove it. And you get two different equations for the first order kinetics. And they will look like, I erased it. If it were first order kinetics, then you would have log of blue equals negative kt, and in this case, k prime, right? Because we're not including bleach in here anywhere. So that has to be k prime, plus natural log of initial concentration. Okay, so you get that equation, y-intercept time k prime for one order of bleach, and then you get it for the second order of bleach. Then you once you determine the full strength K, right? Okay, so let's say that's full strength, and you're going to have another one for half strength. Then you can set up your rate at full strength and your rate at half strength is equal to your K prime full times the blue first order and your K prime half strength blue first order. And if we ratio those two, we'll have two different rates here. We'll have blue cancels out, and then we'll ratio these two. Let's see. Talk myself into a corner. Oh no, I'm ahead of myself. I'm sorry.
I feel like, no, this was not in front of us before, and I feel like it's different.
Yeah. It's on the back side of this one. Yeah, it's on the back side. This one's better. This one right here. Use
I
that.
don't know where you're getting all this stuff from.
Yeah, use that one. So we get this equation here for the full strength. So this is going to be a value. And this is going to be a value. And then we get so now we know what K prime for full strength is. And we know what the half strength, then we get K prime for half strength. Well, what did we call K prime? Well, K prime is equal to that one times that one. The actual K times the bleach. To whatever. Right? So if we have one that's, let's see. Wait a minute, that's not, oh yeah, that's here. Okay, that's fine. So there's the K. And this is full. This is half. K doesn't change. But the bleach concentration does. And the order doesn't change. So we're going to get a value for K prime from the full strength experiment, a value from the K prime from the half strength experiment. The K's, then if we ratio those two,
then the K's cancel out. We ratio these two values, and we have values for the different concentrations, right? We're gonna have a concentration for the full strength, which you calculated, do all that drop stuff. And then half strength will be a different bleach concentration. So this one divided by this one should actually be, this is twice this one, so this should be 2 to the m power. And the k's cancel out, right? So we're going to have this one prime full divided by k prime half. So we have these two values. So we say this one divided by this one, these are real numbers, is equal to this one to that power. And then like before, we can find out what m is based on the power of 2 gives us that value. And that tells us what this is, the order of bleach. Be forewarned, it probably will not be a whole number. It might be close to a whole number. Now, once you know what the order is, then we can use the expression, one of these expressions. So we get that k prime equals k times concentration of bleach for that order and solve for that unknown. That'll tell us what k is, the true value of k. Okay? That was kind of convoluted, but once you get some data, then we can dig into it. And you've got examples here that you can follow along. That's the reason I wrote this thing out, was in such detail. Okay, 3:45. So we can pack up and move in the lab and get some data. I started up the spectrometer already, so it should be warmed up. And I think I set it on blue, just out of habit. But you can check the wavelength on it to see if it's the same as blue in your method. I think. Let me see where it's at. Yeah, second page, top right corner. No, that's not it. Sorry. I was looking for the wavelengths. Yeah. There'll be. There's on the first page.
What we looking for?
The wavelengths. Because when you write your report, you need to be able to report that. It's on the spectrometer. You can just copy the numbers off. But I thought it was in here somewhere too.
I thought I saw it as well, but I'm not seeing it now.
Now, there are places in here for blue and red, but you can just do blue if you want.
Are we only doing one color?
Yeah, I think that'd be best.
So we're not doing all 3 activities?
Well, you're just doing the activities for, is there one in here for red?
I think
No, there's the activities repeated like 3 or 4 times.
there's a trial 1 and a trial 2.
Oh, I see what you mean.
Yeah.
Trial 1, finding the order of the dye. That would just be for the one color. And then trial 2, finding the order of the sodium hypochlorite.
So
That's just for one color.
are we doing activity 1 and activity 2?
Okay,
How many
1,
drops of
2.
sodium and rate law expression?
Actually, you're doing all activities,
Okay,
except just for one color,
just one color.
just for the blue,
Okay.
yeah. Well, I better find those numbers. They're supposed to be in here.
I thought I saw it. I'm not seeing them now.
Yes. Here it is. In the addendum, down here at the bottom in the red box. Blue is 630 nanometers. The problem with that is the spectrometer that I got from Diane, it only does on 5 nanometer increments.
Yeah, it does.
I mean, it's on 5s and it jumps to 5s to 5.
Yeah.
So I set it on
You
635.
can, do it from ones.
Huh?
You can do it on ones if you press down and twist.
Oh, I didn't know that.
Yeah.
Okay, do that. Set it on exactly 630. Because 630 is the maximum absorbance. Yeah, it's in the addendum.
Oh, that's why I only printed the first 5 pages because I didn't know that I needed this.
Yeah. You want another copy?
I didn't know I needed that last few things.
Yeah, I should have handed everybody a copy of this last week. And you would have had everything. Let's see, I'm still recording, duh.